Welcome friends to my YouTube channel. Now on my today's lecture, that is the last lecture of elasticity, I shall do few important numerical problems, okay, related to examination, okay. Now the first numerical is that given that Young's modulus is 7 into 10 to the power 11 dyne per centimeter square, okay, and rigidity modulus it is also given eta, this equals to 3 into 10 to the power 11 dyne per centimeter square, okay. We have to find Bach modulus K and Poisson's ratio, okay. So this is the pure numerical, simple numerical, that is the first formula, that is y equals to 2 eta into 1 plus sigma, okay. So what will be my 1 plus sigma? This is simply y by 2 eta. So this is sigma, this equals to y by 2 eta minus 1. So what is y? 7 into 10 to the power 11 by 2 into 3 into 10 to the power 11 minus 1, okay. So this is 7 by 6 minus 1, that means 1 by 6. So this is the value of sigma, Poisson's ratio, okay. Now we have to use another relation in order to find out k, okay. We know this relation y, this equals to 9 into eta k by eta plus 3k, okay. So we have to use this relation. We know y, this is 7 into 10 to the power 11, this is 9 into eta, 3 into 10 to the power 11 into k by 3 into 10 to the power 11 plus 3k, okay. So this is 7 into 3 into 10 to the power 11 plus 3k, this is simply 27k, and if you do it, okay, the value of k becomes this 3.5 into 10 to the power 11, okay. This is the dyne per centimeter square, okay. If you do just simple calculation, then the value of k that you would get is this, okay. So this is the pure simple numerical question, okay. Now the second numerical of today's lecture a body is under stress along 3 mutually perpendicular directions, okay. Now we have to derive the condition under which the, okay, so derive the conditions under which, okay, strain along z axis is 0 and that along x and y axis are equal. So obviously the body is under stress along 3 mutually perpendicular directions, okay. So suppose this, say this is x and z, this is y. Suppose we apply force P1 per unit area along outward direction along x-axis, and y-axis this outward force is P2, and along z-axis this outward force is P3, okay. So this is y axis, this is z axis, this is x, y, z. Okay. Now due to the force P1, there is a extension along x axis and contraction along y and z axis. Okay. Now similarly, P2 force is acting along y axis, so extension along y axis is this and contraction along y axis is this, and P3 force acts along z axis, so sigma P3 by y, this is minus sigma P3 by y. Okay, fine. Now our condition is that the strain along z axis is 0. That means net strain along z axis is this. Net strain along z axis is this. So this we have to make 0. Okay. Okay, this we have to make 0. So if we make, we don't erase it because I require it later. Okay, so P3 minus sigma into P1 plus P2, this equals to 0. Okay, and from this condition, from which we can write sigma this equals to P3 by P1 plus P2. Okay, now by making this, that is the strain along z axis 0, we arrived at this condition. Now let us see what happens here. Also given that the strains along x and y axis are equal, so we have to make equal them. Okay, so if the strains along y axis and x axis are equal, minus sigma P3 by y, this equals to P2 by y minus sigma P1 by y minus sigma P3 by y. So this cancels. Okay, so if we take common, that is y cancels, so P1 plus sigma P1, this equals to, if we take P2, that is 1 plus sigma. Okay, okay, so P1 by y minus sigma P2 by y minus sigma P3 by y, and this is P2 by y minus sigma Py by y, this. So P1 okay, so if we do x and strains along x and y axis are equal, then we will get this. Okay, P2 minus sigma. Okay, fine. Okay, this is simply, so from which we get sigma this equals to minus 1. Fine, and if we put the value of sigma minus 1, then we get P1 plus P2 plus P3 is 0. So this is the required condition. Okay, the required condition for the strain along z axis to be 0 is that and the required condition such that the strains along other two axes, that means x and y axis, equal is that sigma equals to -1. So at first we have to find out the value of sigma, then we have to put the value of sigma so that all the conditions holds good. Okay, so this is the condition. Now another numerical is that now we have to find the condition, find the condition under which strains along x and y axis is 0. Okay, this is the question. Fine. So this is x, this is y, this is z. So this is p1 by y, this is minus sigma p1 by y, and this is minus sigma p1 by y. This is p2 by y, this is p3 by y, minus sigma p2 by y, this is minus sigma p2 by y. This is minus sigma p3 by y, this is minus sigma p3 by y. So the strains along x and y axis are equal. So first we make the x axis equal, that is equal to 0. p1 minus sigma p2 minus sigma p3 equals to 0. Okay, so from which we can get p1, this equals to sigma into p2 plus p3. Okay, now the second thing, we have to make the strains along y-axis equal, that equal to 0, that is p2 minus sigma p1 minus sigma p3, this equals to 0. Okay, so from which we can easily get p2, this equals to sigma into p1 plus p3. So sigma will be p2 by p1 plus p3. So both are sigma, so we can make these two equations equal. So here sigma is p2 by p1 plus p3, and here sigma is p1 by p2 plus p3. So if we make the conditions equal, then we will get it. Okay, so what is this? That is p2 square plus p2 p3, this p1 square plus p1 p3. So p2 square minus p1 square plus p2 p3 minus p1 p3 is 0. So this is p2 plus p1, this is p2 minus p1. Okay, and if we take p3 common, it would be p2 minus p1, this equals to 0. So this is simply p2 minus p1 into p2 plus p1 plus p3 is 0. So these are the required condition. Okay, so this is the required condition so that the strains along two axes are equal. The condition is either p1 equal to p2 or p1 plus p2 plus p3 is 0. Okay, so these are some numerical problems, and with this chapter I have with this problem I have completed the chapter elasticity. Okay, so if you like this video, then kindly subscribe my channel. Thank you.